Okay, C2IRV back again after a while. Haven't made a video in a while. I've been busy with work, busy with the system itself, and just haven't gotten around to making a video. Didn't think much was really worthy of a video. Except today, with the proof of concept of a little project that I have here. I've spoken to you guys before about GPS locking the 9.6 MHz on the radio thin client radio thin client module, also known as the RTCM, which was something when I had the OCXOs was been working very, very well. You know, I had to do some initial adjustments and compensate for a little bit of temperature changes at the sites, but they've been working actually pretty well. But I wanted to go a step further. I wanted to go further with this. I had mentioned at one point using the Leo Bodner programmable GPS unit. I have purchased one. Actually, it's right here. If I can... Well, you know what? I can't... I'm going to destroy everything on this table. This table's a disaster area. So anyway, that's the unit right here. Is the Leo Bodner GPS device. It's two outputs. I have a program for 10 meg. Oh, now this thing's freaking out. I have a program for 10 meg. And it works extremely well. You can program one of the outputs for 9.6 megahertz. Unfortunately, you can't program it for 10 megahertz and 9.6 megahertz. You can program it if you want for 4.4 or 14.4 megahertz and 9.6 megahertz if you want to try to phase lock Motorola's, like the Motorola Max Tracks or GM300s or most of the other Motorola transmitters. Almost everything uses 14.4 megahertz, so you can do that. And it's a great little device. Costs, when all is said and done with shipping, $212, but the shipping is extremely fast. You'll get it in about 2 days from FedEx. And the reason for the weirdness when it comes to the GPS, this GPS unit, when it comes to programming the output frequencies, when you program output 1, that sets the divide by for output 2, and then it takes the divide by up in frequency. So if you set it to 10 megahertz, it's going to have a secondary frequency of everything above 10 megahertz with, you know, its appropriate divide by, and gets in some really weird numbers. So it's because he only has a single PLL chip in there, which I'm surprised he just doesn't have two PLL devices inside the unit to create two independent outputs. But you know, hey, it's his device, so, and it must serve a great need for that. But for just outputting 9.6, it's great. The reason why I embarked on a different project for creating a standalone phase lock loop circuit that can be clocked to 10 megahertz is to eliminate the need for a second GPS antenna, or having to split off the GPS antenna you have, which you can create circuits for, or you can buy splitters, which are a little pricey. So what you see in front of you has essentially met that need. I can't down. This circuit you see in front of you is a little creation of my own. It's a 9.6 megahertz phase lock loop circuit that is referenced to 10 megahertz. And it is just completed tonight. So you have a 9.6 megahertz out, and this is your 10 megahertz in right over here. And I have this wire here is actually referencing my frequency counter, so I got to move that over. Everything's kind of a little tenuous because, as you can see, it's a disaster area on my bench here. I've been, you know, working on this thing. So the goal for this unit was to have something that everybody could build, was fairly straightforward, didn't require a PIC or any programming of a PIC, and was kind of versatile. You could do a bit with it with some changes to the circuitry. So this is largely, very largely, based off of an old phase lock loop circuit that Motorola had engineered for their MSF 5000 stations. I believe it started with those stations. And this was their high stability oscillator circuit. And what they would do is they would take a 5 megahertz oven, and there was also a channel element, a 14.4 megahertz channel element. And then a circuit very similar to this would phase lock the 14.4 megahertz channel element to the 5 megahertz crystal oven. The way it did that was it divided both frequencies down to 100 kilohertz. It used an exclusive OR gate and used it as a phase detector. And then the output of that OR gate would then go to a loop integrator, which would output a rippled DC voltage. And then that DC voltage would be used to adjust the frequency on the channel element. And then the channel element was fed back in, creating a closed loop, or a phase lock loop. So that circuit was very simple, used all TTL logic, and was easy to use that circuit as the basis for what I wanted to do. And it's not very complex, as you can see here. I mean, there's not a whole lot of parts on this board, for what it does. To give you an overview of what this really does, is we have over here 2 transistors. One acts as an amplifier, the other one acts as a wave shaper. And essentially what it does is, the amplifier is nothing more than really a buffer, and then the wave shaper kind of squares off the signal a little bit, and then it's fed into this TTL logic. This is a divide by 10 counter, which then divides my 10 megahertz down to 1 megahertz. And then out of that divide by n counter goes to another, divide by 10 counter. Out of this divide by 10 counter, it goes to another divide by 10 counter, which then divides it down further to 100 kilohertz. And that 100 kilohertz is fed into this chip, which is a quad exclusive OR device. And on the other side of it, okay, we have one of my, 9.6 megahertz crystal ovens that I have a bunch of. I bought a bunch of them. And that goes through essentially the same circuit, a buffer and a wave shaper. It goes into a divide by 12 counter, which then divides the 9.6 megahertz down to 800 kilohertz. And then we go to a divide by 8 counter, which divides it to 100 kilohertz. And then they're fed to the inputs of the exclusive OR. Then the output of that exclusive OR goes to a transistor, which acts as an amplifier, and then you also have these 2 resistors and caps, which give you that pulsed DC output from the pulse train. And that pulse train is at 200 kilohertz. And that DC output gives you your control voltage. So far it's been locked on, and I have, let's get this up here. You can see it. Oh, what a mess. That's my my frequency counter, and that is the output of the 9.6 megahertz oscillator. This right now is being referenced to the 10 megahertz off the Leo Bodner programmable GPS oscillator, which is also feeding the 10 megahertz into the circuit. So that, because of that, this is telling me that this is truly, that this circuit is truly phase locking the crystal oscillator to the 10 megahertz input. So it wanders a little bit. I was a little concerned that every once in a while this would go off frequency by a couple of hertz, like 1 or 2 hertz, and then it would walk itself back in. And so far, as time goes on, that's been happening less and less and less, and every time it does happen, it's to a much lesser degree. So I believe it's that the crystal heating and cooling itself with the heater to get itself to kind of a steady state. And really, most commercial GPS oscillators, GPS-locked oscillators, really need at least a couple of hours to really stabilize. So this has been doing very well. So now, let's see if I can do this. I can show you on the screen all the waveforms. This may be a little difficult, but I'll try. So, let me see. So pin 1 on this unit is my input to the oscillator. I gotta move that up. It kind of shapes it a bit, it kind of squares it off on the bottom a little bit. Okay. Now that's our input to the first chip, which is a divide by 12. So what is the output of that? That is pin 12. So if I go to pin 12, that is my output of pin 12, which is going to be approximately, well, not approximately, it's going to be 800 kilohertz. So then if I turn this down, then the output of our divide by 8. Oh, get back on there. And it's 100 kilohertz. Right there. Now, the two inputs to the exclusive OR, that's the input from the 10 meg source, and that's the input from the 9.6 megahertz source, and this is its resulting output. I got a little bit of a high frequency riding on there, but that does not seem to affect it at all. And actually, I saw that. I was able to compare this circuit directly with the Motorola unit, and it does roughly the same thing. So, since that's all being rectified to DC, it's not a big problem. So, and then if I go to my DC, you see a little bit on the output, but it doesn't actually affect it at all. I might actually put a cap in there just to kind of get rid of it. Some noise, it looks like. So, but yeah, I might actually put a capacitor on that to try to get rid of some of that, make it a little cleaner. But so far, the circuit's been operating exactly as intended. So, and besides that, our phase voltage, our oscillator control voltage, which actually, I don't know if you can see my, let me see if I can zoom this. Oh, I can't. Oh, I can, I just gotta do this. There we go. First time I did that on this phone. So this is our oscillator control voltage. Right there, it's about 4.49. And you know, right now it's locked. Now, let's watch. Let's see what happens when I unlock this. Okay, that's the. Doesn't move much. I still have about 4.8, but that's because I'm most likely still getting something through. I'm still getting a little bit through the exclusive ore. If I lose my 10 meg. So, because right now I'm what? Actually, only 0.3 hertz off. Whoop. My camera work isn't really good. I'm not a cameraman, so forgive me. Yeah, 0.3 off, so yeah. 0.3 hertz off. So, plug this back in. It should start to lock again. It's kind of going to go out of whack for a while. It's at like 5.5, 5.4, 5.2. Oh, now it's going down. Now it's going up again. So it's trying to walk its way in. Like 3.7, 3.8, 3.9, 4, 4.1, 4.2, 4.3, 4.4. Now 4.6, 4.46, 4.47, 4.48, 4.49, 4.5. So it's at 4.5 now. So it's it walked its way right back in after losing the 10 megs. So I would have to say that's success, at least in my book. I still have more to do on this. I want to create a an out of lock indication so that I can tell when this oscillator is out of lock. I mean, one of the ways you can do it is, you know, drag a frequency reference with you, or I'm sorry, a frequency counter with you. So this is, I have to say, extremely good news. So besides that, let me take this thing back out. And I'm supplying this with 5 volts and 12 volts. Right now, it's drawing a total. I have the power supply set at 15.1 volts, and with it all warmed up, it draws about 0.3 amps or 300 milliamps. The whole deal. When the oscillator's cold, it draws about 750 milliamps, maybe around 8. So it doesn't draw a lot. This is a 1 amp 5 volt regulator, just a 7805, and this is a 2 amp 12 volt. That is a what? A 70 an LM. God, I can't read it. Hang on. An LM 1085. So got everything from DigiKey, and it's working well. The only thing I might wind up doing is I'm not buffering this 9.6 meg out, mainly because this oscillator puts out like 3 volts peak to peak. It's like 3 volts, 3.5 volts, something like that. And I found out that the this thing will tolerate loss down to 2 volts. So, but yeah, it's something I'm probably going to have to buffer, I'm thinking. But I don't know. we'll give it a shot. Anybody have any questions, comments? I have the schematic for this available. If anybody wants to see it, you want to build it yourself. That's why I did not go with a pick or anything, just to make this very, very simple for somebody who wanted to build it themselves. This is more of an RF guy, RF-centric thing here. And I'm also not the greatest at implementing picks and stuff. I'm not the world's best coder, so. But I do realize something like that would make this circuit a little bit more versatile. But this is quite a bit simpler for most people. So this will essentially allow you to simulcast your RTCMs and make it a little bit more maintenance free. Also make it a bit more accurate. So I didn't have to institute anything special. Anything special for this oscillator as far as the voltage that comes out of here. Motorola has this fetish with using 9.6 volts for everything, and a lot of this circuit was powered by 9.6 volts. I did away with that, and some of the stuff that was powered by 9.6 I powered with straight 12. And this circuit, this integrator circuit, you know, needed to you know, it produced 0.5 to 2.5 volts, which was considered interlock. And I kind of figured if I fed this with 12 volts directly, which I calculated the currents to make sure it wouldn't blow anything out. It's minuscule. It's all microamps. It has more than enough voltage to lock this oscillator. This oscillator, these guys is like between 4 to like 5.5 volts, depending on the one you get. In fact, the ones I get from eBay are marked, which is helpful. Let me get a couple here. Like this one says 5.05. This one says 4.07. So they seem to work pretty well. They even mark, you know, whoever's selling these things, they even mark the you know, what's where. So, but originally I was planning on putting a small 100K potentiometer in here to trim the voltage, and part of that was in case the phase lock loop couldn't pull the voltage low enough to lock this. So anyway, let's show you some of the. Let's show you. I don't know. Actually, I don't know if I showed you the pulse train output. Yeah, I think I did. Anyway, I'm getting ahead of myself. This is kind of an impromptu video. It's getting kind of long too. Once again, if anybody has any questions or if they want the schematic on what I've done so far, I'd be more than happy to provide it to you. I use ExpressPCB's CAD software. It's pretty sparse, but it works for most things. You know, their library, you have a fairly large library of components, but some of them I had to create. Actually, had to create the SN74LS93, which is what I'm using as my divide by 8. It didn't exist, so I had to create it. Eventually, I've been working on it. I want to create a board for this, a PCB. That would be a lot. Well, let's lift up the ugliness here. Ooh. Get my thing off. Oh my God! Can't believe this thing even works. Look at this. Look at this thing. Oh God! I can't believe it even works. There's a lot of people holding their forehead right now, going, "Oh my God! Look at that! Look at that garbage under there." Oh man! But it works. It's a mess, but it works. So let me put my scope back on here. Probably gonna freak out. Yeah, it did. kind of did. Yeah, it does some weird things when I move this around by hand. And I'm not sure why. Like now it's kind of... It flew out of lock too. It might be the connection to the GPS, which might be coming out. Oh. Voltage is kind of all over the place now. I'm not sure what it's doing. Is it locking up? Yeah, there's a lot of stray things going on here that shouldn't be happening because of, you know, this board being open. You know, we're not exactly practicing some very good RF practices here. So this thing's kind of flying all over the place. Not sure why, but it's because I moved it. It's because all this stuff's kind of, you know, haphazard. But oh, what's going on the radio? Anyway, so that's it for today. Still more work to do, but it does work. So I'll catch you guys later.